And when curvature radius is very small, like here, it's nearly the size of the neutron star, the pair multiplicity is huge, nearly for the whole range of magnetic fields and the whole range of acceleration potential. Now I go to observational evidences, and in observations we see the main cloud of radio pulsars here, and there are a number of strange sources like central compact objects, which are quite unusual because they are among pulsars, so objects which emit radio, both recycled and just old radio pulsars. On the other hand, the central compact objects are associated with nebula, so they should be young, and they emit a lot of thermal radiation. It's also an indication of their young age. So what can go wrong and why they don't emit radio? So if you look at the observational evidences for pulsar to shine as a pulsar don't shine, there is a famous death line, which is just here, and it should correspond to dipolar magnetic field. But if the dipolar magnetic field is here, when the curvature radius is large. But in principle, if the curvature radius is smaller and comparable to the neutron star radius, you can move this death line from the middle of the pulsar cloud a little bit further away, and it seems to be more or less realistic. It turns all the pulsars stop here. This region between dipolar and non-dipolar death line is called death valley, and CCOs are basically somewhere in this region. And for this reason, it was suggested that CCO experienced some episode of fallback when matter goes after the supernova explosion back to the surface of neutron star and pushes the magnetic field inside, decreasing the dipolar strength. But again, they are above the normal death line. So their dipolar strength is enough to emit radio. So maybe the problem is that their multiples are suppressed much stronger. And the aim of this work is to study how high-order multiples evolve and can they survive the fallback episode. To do so, we use the code developed by Pons, Miralles, and Gebhardt for magnetothermal evolution in the crust of the neutron star. So basically, it's a solution of these two coupled equations on a grid. The first term in the equation which controls the magnetic field evolution is a resistivity term, which says how our crust is not perfect, why magnetic field should decay. And the second term is the whole term. It corresponds to the redistribution of the magnetic field and interaction between poloidal and toroidal magnetic field. So, and here the result of our simulation. Our initial condition is what we take a dipolar magnetic field and strong multipolar magnetic field. In this particular case, it is L10. So you can find something like 10 poles at the surface of the neutron star as the initial condition. But after we put a fallback, it is during 1 year, and the integrated amount of matter is 10 to the minus 3 solar masses, which can vary, of course. The fallback is spherically symmetric. And so if I start the simulation, just after the fallback, the poloidal field is pushed inside the crust, and it generates the strong toroidal field very fast. It is shown with a color. And after a while, the interaction between poloidal and toroidal field pushes the poloidal field back, and it reemerges, keeping its structure on the surface. So we still can find these 10 poles at the surface. So if I show this result more quantitatively, here's the amplitude of different harmonics comparatively to their initial value. So first of all, I need to say that we reproduce the previous results obtained for reemergence of a dipolar magnetic field. So when we have a dipole, after a fallback episode with 10 to the minus 3 solar masses, it decays approximately 2 orders of magnitude, and it stays in the crust for 10 or, well, for nearly 100,000 years, and slowly re-emerge back to the surface. But when we put high-order harmonics like L6 or L10, L15, all these harmonics were suppressed much stronger by fullback. So if we are somewhere at this moment, 100 or 1,000 years, and we try to measure the curvature of open field lines, we could think what the magnetic field in this neutron star is really dipolar one, because a dipole is really the strongest harmonics here. But after a while, these high-order multiples will start to reemerge, and for some of them, for example, for L10 and high magnetic field, these harmonics reemerge even stronger than it was at the beginning. So what does it mean for pulse remission? This is a view on polar cap region of a neutron star on around the north magnetic pole and south magnetic pole. And red lines show some of the dipolar magnetic field lines, and magenta lines correspond to the open field lines. So acceleration would happen only here. And if I start this video, at some point the curvature of field lines in this region would change dramatically at the moment when high-order multiples they would start to reemerge. So it happens somewhere around 10,000 years, maybe few multiplied to 10,000 years. And it gives a very good site for high multiplicity. So like at this moment, for example, these lines are very curved here. So the opacity for gamma ray photons is getting very strong, or yeah, maybe I should explain it at this plot. So what's going on more quantitatively? We have actual curvature of open field lines at different distances from the polar cap, at 100 meters and 1 kilometer. And this is shown with black lines. At first, the curvature of open field lines is smaller than dipolar one, because it is our initial condition. But after the fallback, it returns exactly to the dipolar curvature, which corresponds to 100 radius of the neutron star. And we can also ask such a question: which curvature do we need to emit as a radio pulsar? And of course, it depends a little bit on model, so that's why we assumed 100 meters and 1 kilometers. And at these distances, we can measure, we can ask which curvature of open field lines provide enough particle generations or enough multiplicity. So at 1 kilometer it is a red line, and at 100 meters it is a blue line. So when the field is dipolar and it is suppressed to orders of magnitude, the acceleration potential is getting smaller, so the actual curvature which you need to start emitter radio is very small. It's around the size of the neutron star. But all the higher order multiples are suppressed, so you cannot emit radio at this region. But at some point, first, higher order multiples start to reemerge, so that's why this black line, actual measured curvature of open field lines, goes down. And on the other hand, at some different time scale, dipole start to reemerge. And you see what curvature of open field lines is not necessary to be so small anymore, because acceleration potential is getting larger. And at some moment they intersect. So this neutron star start operating as a radio pulsar probably. Of course, this is a theoretical picture, and it should be verified in some observations. It was already a few searches for old radio pulsars here. I don't say they look as old because their spin down age is large. But Such candidates should have a large thermal emission with temperatures around million kelvins or so. And such searches found no candidates at this point. But in our scenario, we expect that a temperature might be smaller because operation of our radio pulsar starts when small harmonics are emerging, not so strongly dependent on the general dipolar magnetic field. So we put an XMM Newton proposal to observe these 3 radio pulsars with large exposure. The main criterion to select this radio pulsar was their large spin down H and some associations with OB associations. So they are quite small distances. Unfortunately, still not yet observed. So I go to the conclusion now. So small-scale magnetic field can survive the full-back episode. This is the main conclusion. And approximately after 10,000 years after full-back, this reemergence happens. But before, the external magnetic field looks exactly as dipolar one. So thank you for your attention.
Thank you. Any question or comment?
How would your conclusions be affected if instead of a spherical fallback, you have a fallback disk?
Well, basically it depends how much mass we accrete in the polar region. So if no mass is accreted in the magnetic pole region, then probably this multipole survives anyway. But if it is a larger amount, then reemergence timescale might be different.
Thank you.
In your simulation, you started with the same intensity for each of the multipoles. Is there any reason to start with the same?
It was not exactly this. Did you ask about intensity? Or?
I mean, the plot you showed the evolution of all the components with time. No,
this one.
Yeah.
Yes. So it is a normalized one. So I divide intensity at some point at the initial intensity. So they are not exactly the same. I mean, actually we choose high-order multiples to be 1.5 times larger than dipolar component at the beginning.
Okay, so it's
yeah, but in principle it is an arbitrary choice, indeed.
Okay. So it could mean that even a quadrupole could be higher than the dipole.
Yeah. So we really wanted high-order multiples to influence the curvature of open field lines.
Thank you very much. So I think we can switch to our next speaker now. And let's thank our speaker again.
So the title of my talk is Quasi-Stationary Evolution of the Magnetic Field in the Course of Neutron Stars. And this work is made in collaboration with Yelena Kantor and Dima Afingame. So let me set the problem first. The magnetic field in neutron stars ranges from 10 to the 8, 10 to the 16 Gauss. And to interpret observations from the very diverse classes of neutron stars, it's important to study the evolution of the magnetic field with time. And here we concentrate on the evolution of magnetic field in the neutron star core. So what should we know to model the evolution? According to Faraday law, we need to know the electric field. And this electric field in the core, for example, it depends on many different quantities, for example, on particle velocities, on chemical potentials, perturbations of chemical potentials, and on magnetic field itself. And it's important to stress that these quantities also determined by the magnetic field. So it's a complex problem to determine all these quantities. So our aim is for a given specified configuration of the magnetic field to calculate accurately all the quantities that determine dB over dt, which means that we are going to prepare a basis for modeling the magnetic field evolution in the core. So there are quite a lot of works in this direction, and some of them are listed here. And they mainly follow the approach to this problem pioneered by Galbraith and Reisenegger in 1992. And the most advanced work developing the ideas of GR92 is a recent paper by Passamonti et al. And although these papers are very enlightening, the validity of some approximations made in these references remains unclear to us. And so our purpose was also to check these approximations and to think on them. So for simplicity in this talk, I consider the simplest possible core composition. Neutron star core composed of neutrons, protons, and electrons. I neglect the superfluidity and superconductivity effects. There is also no general relativity effects. And I assume that our star is actually symmetric, so the magnetic field just depends on r and theta coordinate. Then the general equations which govern such a relatively simple system are written here, and they consist of the momentum equation for each particle species, for neutrons, protons, and electrons. Here, U(a) is the velocity of particles, mu is the chemical potential, and for example, this is a term due to friction forces between different particle species. So the second equation is the continuity equations for each particle species. And here, this is a source due to non-equilibrium beta processes, which are induced by the magnetic field. Magnetic field perturbs the system out of beta equilibrium. So the next equation is just a Poisson equation for gravitational potential. This is a Faraday equation, this is an Ampere equation, and this is a quasi-neutrality condition. So these equations are still difficult to solve, and we need to make some approximations. So these approximations are the same as in the classic paper by Galbraith and Reisenegger. So first of all, we neglect small nonlinear terms in these equations, this one. The second, we will use, we adopt Cowlin approximation, which means that we neglect the perturbation of gravitational potential. Third, and most important thing, is we assume that the system is quasi-stationary. What does this means? That the magnetic field, we assume that magnetic field is the only driving force that distorts the system from equilibrium. This allows us to neglect time derivatives in all respective equations, in momentum equation and in the continuity equation. So the resulting equations are much simpler. And these equations contain also the total force balance equation, which is just the statement that gradient of total pressure equals to the Lorentz-Forens density. So these equations can be solved, and it's suitable to discuss the solution in terms of these quantities. The first is perturbation of neutron chemical potential induced by the magnetic field. The second quantity is chemical potential imbalance. Because of this quantity, we have non-equilibrium beta processes in the core. And the third quantity is the flow velocity of the fluid as a whole. And the fourth quantity is the diffusion velocity of species A, which is just relative velocity of particles A with respect to the flow of the fluid as a whole. So it can be shown that knowledge of these quantities fully determines evolution of the magnetic field. And we calculated them all except for the toroidal velocity, flow velocity of the fluid, for which we derived a differential equation, but still haven't obtained a solution. So let us discuss the solution. First of all, let's discuss the chemical potentials, neutrons and imbalance of chemical potentials. So they can be found from the total force balance equation. The solution, this equation can be solved, and the solution is presented here in the matrix form. Here we see the components of the Lorentz force density, and all these guys are known, and only interesting quantity here is the function zeta, which is unknown, but it can be shown that it's unambiguously defined from the requirement of regularity of the flow velocity, u, at the magnetic poles, at any coordinate error. This requirement gives us a differential equation for the function zeta. So, in fact, we know how to calculate perturbed chemical potentials. Now, the interesting property of this solution is that if we expand these chemical potentials in Legendre polynomials, then all the components in this expansion with L larger or equal than unity are fully specified by the magnetic field, which means that they are, for example, do not depend on temperature. This follows just from the form of the solution, and they do not depend on this zeta function. So this is in contrast to the solution obtained previously, for example, in paper by Goldreich and Reisenegger, in which all the components of perturbed chemical potential depend on temperature. So what is the reason for such a discrepancy? We believe that the results are different because of the approximations made in the previous works. For example, Goldreich and Reisenegger assumed from the very beginning that neutrons are immobile. In turn, Passamonti et al. Assumed that either baryon velocity is zero or the matter is non-stratified. So our analysis shows that these assumptions, and I will talk about it a little bit later, that these assumptions are not actually valid, and baryon and neutron velocity are not small and can be neglected generally. So, to calculate numerically chemical potentials, we need to specify, and all the quantities, we need to specify, of course, the magnetic field. And we choose the same models of the magnetic field as those used by Passamonti in their paper. And this allows us to compare our results with theirs. So here I present an example, numerical results for the perturbed imbalance of chemical potential. Here I show our result, and this is the result taken from the paper by Passamonti et al. Here you see a half of the star, and by different colors we show the magnitude of delta mu in units of temperature. And temperature here is taken like this, and the magnetic field at the magnetic poles is 10 to the 14 Gauss. So you see that generally the magnitude of delta mu and the structure of the plots are very different. This is so we discussed the perturbations of the chemical potentials, and next let's discuss the diffusion velocities. They can be found from these three equations, provided that this delta mu n is already calculated. So the first equation is just the statement, is the force balance equations for neutrons. It's just the statement that gradient or partial pressure of neutrons is balanced by the friction force between neutrons and protons. And these we neglect here the friction force between neutrons and electrons, which is much smaller. The second equation is simply Ampere law. And the third equation just follows from the definition of the flow velocity of particles. So these three equations allow us, linear equation, allow us to calculate diffusion velocities. So, and it's interesting to compare our results with those of Passamonti because, however, instead of the diffusion velocities, these authors calculated the so-called ambipolar velocity, which is defined like this. It's proportional to relative motion of protons with respect to neutrons. So here we present our result for the ambipolar velocity, and this figure is taken from the work by Passamonti. Here arrows shows the direction of the ambipolar velocity. It's half of the star. And magnitude, here I plot the logarithm of ambipolar velocity in kilometers per megayear. So different colors show this quantity. And you see that by comparing these figures, you see that the topology of the ambipolar velocity is very different, and ambipolar velocity calculated by Passamonti et al. Is smaller by a few orders of magnitude, which is quite a large discrepancy. Okay, so we discussed these three quantities, and then the most interesting one, which was not calculated up to now in the previous works, is the flow velocity of the fluid. So how to determine it? First of all, let us determine the r and theta components of the flow velocity. They can be determined from the neutron and proton continuity equations. Here are they, and we can solve them and determine UR and divergence of U. This is again a linear equation as a functions of already known quantities, as functions of diffusion velocities and perturbations of chemical potentials. So we know them, and since our problem is actually symmetric, there is no phi component in the expression for divergence of U, phi component of the velocity. So we can determine from these guys theta component, which is given just by this integral. So we have an analytical expressions for the r and theta components of the fluid velocity, and phi component will be discussed a bit later. So here I present the results. This is, here I show r and theta components of the fluid flow velocity in units of 10 to the minus 12 centimeters per second. And for comparison, I also present the diffusion velocities for neutrons and for protons. Again, colors show the magnitude of the diffusion velocities, and arrows show the direction. And you see from these figures that the rather important result that the flow velocity is substantially larger than diffusion velocities. And this clearly indicates that shows that approximation of vanishing U is incorrect, in our opinion. So, and what about toroidal component of the flow velocity? How could we determine it? The idea is to look more carefully at the quasi-stationary balance equation. We already saw it. It depends on the perturbations of chemical potentials. But they are, because our problem is quasi-stationary, they are the functions of r and theta only, which means that the gradient of these chemical potentials can't have a component along the phi. What does it mean? This means that the magnetic field configuration should be such that the phi component of the Lorentz force vanishes, because it cannot be compensated by the gradients of chemical potentials. Okay. But the magnetic field changes with time. For example, it dissipates. So this means that to maintain quasi-stationarity in the course of field evolution, we have to require that not only phi component of the Lorentz force to be zero at any moment of time during its evolution, which is equivalent to condition that the time derivative of this force vanishes. So if we employ Faraday equation and the definition of the Lorentz force density, then we can transform this condition to the following form. And here E is the electric field in the laboratory frame, and it can be generally related to the electric field in the comoving frame by this well-known formula. And E comoving is the electric field in the frame in which fluid flow velocity vanishes. So comoving frame, electric field in the comoving frame, we already calculated because it's known functions of perturbations of chemical potentials and diffusion velocities. We know it. So we can substitute this expression here and obtain a differential equation for toroidal velocity U-phi, which still to be solved because it's a rather complex equation. So we are working on its solution now, but don't have the results. So I'm finishing. We have calculated all the quantities except the toroidal component of the flow velocity that allow us to self-consistently follow the quasi-stationary evolution of the magnetic field in the neutron star core. So we have all ingredients to follow this evolution for the first time. Our results differ quantitatively from the results available in the literature, e.g. in these papers. In particular, the flow velocity turns out to be non-negligible, larger than the diffusion velocities. And this is contrary to what was assumed in the previous works. The toroidal component of the flow velocity plays an important role in maintaining the quasi-stationarity of the system. So it guarantees the quasi-stationarity. The approach presented here can be extended to include the effects of superfluidity and superconductivity, additional particle species, non-axisymmetric magnetic field configurations. And more details can be found here, and we are now preparing one more paper on this. So there are also so our nearest plan is to calculate UV toroidal velocity, try to model the quasi-stationary magnetic field evolution, and in this way there is some problem. We need to think on how the presence of the crust will affect the results, and probably to apply the results to magnetars. Thank you.
Thank you.
You mentioned something about the assumptions of previous authors, but actually at such temperatures protons are superconducting, so the assumptions of the present paper is just incorrect.
No, the point is the degree of superconductivity or superfluidity depends on the magnetic field. For example, in magnetars, if you take 5 times, for example, 10 to the 15 Gauss, then
You
the...
mentioned 10 to the 14.
Yes, I from the very beginning, I said that we consider the simplified simple problem just because there are incorrect results, as we believe, even for this problem. So before to move forward, we need to understand what is what in the simplest situation.
And it's not surprising that your results do not coincide with the correct ones.
No, because these authors also consider non-superfluid and non-superconducting matter.
But someone considers superconducting.
No, we compare with, they consider various possibilities, and one of these possibilities, they consider normal matter. I can show the reference during the coffee break.
Yeah. Thank you. More questions?
Yeah, you showed the chemical potential imbalance, but did you also include weak processes, or are they
Yes,
just
of
slow?
course.
Yeah,
And I mentioned it. So we include the source in the continuity equations due to beta processes, yes. And it's a function of this imbalance of chemical potentials.
Okay. More questions? No. So let's thank our speaker again and move to the next one.
Thank you. Hello. Here in this talk, I will mention about the critical strain angle, which is significant parameter for the crust quake in the neutron star. Neutron drift density separates the crust into two regions. In the outer region, the ions arrayed in a probably BCC Coulomb lattice, which is immersed in a gas of degenerate electrons. And above this density, nuclei becomes very neutron rich, and there are also free electrons and neutrons. Because of the neutron-neutron interaction, there is a superfluid, there is a BCS superfluid states, and electrons and screening effect is negligible because the electrons are relativistic here. At the highest densities, which is about 10 to the 14, nuclei start to touch and maybe merge, and Coulomb energy is comparable in magnitude with the surface energy of the nuclei. And spherical lattice turns into distorted into the elongated shapes which are called the nuclear positive phases, spaghetti-like rolls and lasagna-like slabs. Crust quake. After glitches, glitches were firstly observed, which as an abrupt increases in the spin frequency and spin down rate, the crust quake scenario was proposed. According to this model, as the neutron star spins down, it wants to become more spherical, and oblate crust develops strains, and as the strain has a critical threshold, it eventually breaks, and because of the angular momentum conservation, the reduction of the moment of inertia, leads to spin up. There is also another effects, which are the internal electromagnetic strains, or the vortex lattice interactions, which can cause the crust quake. Crust quake explains the size of small glitches, like in Crab pulsar, while it is inadequate for larger glitches, like in Vela glitches. There need to be some more agent, which is the superfluid component. So, according to this, the superfluid component amplify the vortex unpinning, while the crust breaking plays a role as a trigger mechanism. In the history, there was some attempts to estimate the critical strain angle in the neutron star crust. In the very early work of Smoluchowski and Welch, it was estimated as 10 to the minus 5, 10 to the minus between 10 to the minus 5 and 10 to the minus 3 by doing analogy with terrestrial crystal. But neutron star crust is not like a terrestrial matter in which the screening is negligible, and because of the long coupling of the pure Coulomb interaction, there can be a kind of plastic deformation up to a large strain angle. Based of this idea, Ali Alpar and David Pines in 1985 predicted that the critical strain angle is between the 10 to the minus 1, 10 to the minus 2, 10 to the minus 1 by related the Pine structure constant, and also in the recent works of the Horowitz-Kadau and also Hoffman and Heil, it was found that the critical strain angle is 10 to the minus 1 based on the molecular dynamics simulation, but they found the critical strain angle for one specific layer, for the outer layer of the crust. So the large critical strain angle means that the crust is really strong. So it can sustain a very large mountain on the surface. So the gravitational wave radiation can detectable because of this. What we did in this work, we estimated the critical strain angle for all layers of the neutron star crust. Our hypothesis is this. If the dimensionless value of the critical strain angle is at the order of the Coulomb potential energy divided by the total kinetic energy in one Wigner-Zeiss cell, then we calculate the total Coulomb potential energy and the relativistic kinetic energy of electrons in one Wigner-Zeiss cell, and we directly divide them, and also we calculated all of these critical strain angle for different nuclei geometries, which also included the pasta phases. After doing calculation, it is seen that the critical strain angle for all geometries is scaled with the fine structure constant, as you see here, and fine structure constant, and the charge or the charge densities, and also the microscopic length scales, which are the size of the nuclei and the size of the nuclei, and also the size of the Wigner-Zeiss cell. We took we took the value of the microscopic length scales from Ida and Maruyama et al. For the inner crust, and from the Shamalahan cell for the outer crust, and found the numerical values for the critical strain angle all along the neutron star crust. This is our result. As you see here, this is the critical strain angle as the baryon density increases. As you see, the critical strain angle is at the order of the 10 to the minus 1 in the outer region, while it can reduce to 10 to the minus 2, 10 to the minus 3 in the inner region. And also, our estimation for the outer crust, which you can see here, our estimation for the outer crust is in agreement with the the molecular dynamic simulation works of Horowitz-Kadao that obtains the critical strain angle for some polycrystal orientation. So our result in this work is crust is stronger in the outer layers, and crust quakes probably originate at the innermost regions of the crust and may propagate toward the surface. So this is also consistent with the idea that the superfluid component amplify the glitches in the inner crust after crust quake takes place. So we also estimated the strain amplitude of the gravitational wave radiation. As you see here, the strain amplitude is related with the angular velocity of the star and the distance of the star from us, and as well as the quadruple moment here, which also depends on the critical strain angle. In other works, when they calculated the quadrupole moment, they took the critical strain angle, which is constant. But here, we took the critical strain angle as a variable in the outer crust and find the quadrupole moment according to this, and these are our prediction, and these are the upper limits of the LIGO, and it is seen from here that our prediction is almost at the same order, almost at the same order of the upper limit of the LIGO, which is very interesting because if our prediction is true, the advanced LIGO is getting close to observe the gravitational wave radiation. Finally, I want to talk about the minimum glitch size in CREP observed by the Espinosa et al. And our explanation for this. What Espinosa et al. Did basically is they uncovered the minimum glitch sizes from the timing noises. So before this work, there hasn't been known whether there was a minimum glitch size. But this works said that there is this work said that there is a smallest glitches which can uncovered from the timing noise. So this gives us the opportunity to investigate the minimum glitches in terms of the crust quake as a trigger mechanism. So what we did, is we relate the minimum glitch size with the moment of inertia where the crossquake takes place. And by introducing some geometries of the crossquake, we relate the moment of inertia with the place size, and also we relate the place size with the number of vortices, which participated in the glitch. So, here it is important that the number of vortices participated in the glitch are very common for the different sizes of the glitches of Vera, Crab, and other glitches. So before this work, it was not known where this common number of the vortices comes from. But now we propose that this 10 to the 13 comes from the plate size, which can be related with the critical strain angle here. So it is important here that critical strain angle is at the 10 to the minus 1, which is quite strong, gives us the number of vortices participated in the glitch at the same order, 10 to the 13. So this common number is about the crossquake as a trigger mechanism. So we conclude that scales of cross breaking and vortex unpinning are explained by the critical strain angle. Here are my summary. Critical strain angle is a significant quantity which determines the size of the broken plate and number of vortices. And the estimate of the critical strain angle scales with the fine structure constant, charge or charge density, and microscopic length scales of the nuclei and the lattice, and also the geometry of the lattice. We conclude that the crust is stronger in the outer layer, and the number of the vortices participated in the glitch is typical for all small and large glitches analyzed so far in terms of vortex unpinning, which points out that a particular scale of the glitch trigger. So 10 to the 13 is about the glitch trigger. The coincidence of the number of vortices is highly suggestive and can be explained in terms of the cross breaking with a typical plate size and the critical strain angle, which is at the order of the 10 to the minus 1 in pure Coulomb lattice. Okay, thank you.
I see one question there.
So you say that 10 to the 13 vortices is typical for both small and large glitches. Can you explain how it can apply to both? I would have expected a large glitch to involve more vortices.
For example, in the Vela glitches, after model fitting by using the vortex creep model, it is also found the 10 to the 13. And also in the very recent work of for Pulsar 1119, we also used the vortex creep model to obtain the number of vortices, we also found the number of vortices participating in glitches 10 to the 13. So regardless of the size of the glitches, the order becomes the same. So we propose that it is about the triggering.
Okay, thank you. I propose to switch to our next speaker. Well, okay.
There is also
Who is
one
also-
question.
who also
May I ask?
yeah, okay.
Probably a comment. First, results by Horowitz-Kardau can be applied at arbitrary density. Next,
Yeah.
molecular dynamic simulations, which aim to discuss the property of critical strain for this depends on the temperature, on the shear velocity, or deformation timescale, was studied in my paper in collaboration with Horowitz. We also have another paper when we study specifically the very small dependence on the composition, depends on the screening length of the electrons. So there is the critical strain is well studied by direct molecular dynamical simulations, and the answer is the critical strain is 0.1.
But now I think, molecular dynamical simulation can be applied for all layers, but we propose that it should be applied right now. Excuse me? Done? Okay.
Okay, so maybe, I don't know, maybe you can discuss later.
we can discuss.
And, okay, short question.
Short question. What is the strain for the pasta phase, for the lasagna phase, for the one-dimensional?
We don't expect breaking in the lasagna phase, because it is one-dimensional lattice. So we cannot. So we found a value for the critical strain angle, but it is meaningless. But for the two-dimensional, it can be broken, of course. So, okay.
Okay, so let's thank our speaker again and switch to the final talk of this morning session.
I will talk about a completely different topic, which is associated with R-mode instability. As far there are no other talks on the R-mode instability in this conference, I will start from the very beginning. And what is R-mode instability? R-mode instability is a particular case of so-called Chandrasekhar-Freeman-Shunted stability. It is rather famous, and it is instability associated with enhancement of the mode by emission of the energy in form of gravitational waves. How emission of the energy can lead to the instability? Answer is rather simple. First, everybody knows what uniform rotation and given angular momentum correspond to the minimal energy of the system, which is rotational energy. Where we can also define the excitation energy, which is difference between energy of the system minus the rotational energy. The gravitational radiation removes energy from the system and also angular momentum. And these quantities, the rate of change of the angular momentum of energy, is coupled by this simple relation, which is the frequency of the mode and this is multipolar number of the mode. And we can just put this equation to this one and calculate the rate of change of the excitation energy. And we got this number. It's very simple arithmetic operation. And as far as we emit gravitational waves, this quantity is negative, and to get the instability, we should enhance the excitation energy. This quantity should be positive. And to do so, the two conditions should be false true. And this is the conditions which was derived by Friedman and Schutz many years ago within very long and complicated mathematical theory. And this is the condition of centrifugal Friedman-Schutz instability. And the energy source for this instability is rotation energy. This is the budget of the Armada instability. The pollen comes from the rotational energy, and this rotational energy divided to two parts. One part is emitted with gravitational waves, and one part is invested to the mining of the rotational energy, to the enhancement of the mode. And what is known about R modes? First, for Newtonian star, one can obtain the analytical solution for the R modes. The frequency for the m equal to 2 modes is this one, and the perturbation of the velocity given by this one. This mode takes place only in the rotating star. If we look to this instability condition, we see what this holds true. This means what, strictly speaking, in absence of dissipation, the R mode should be unstable at any rotation rate. Of course, the real neutron star have some dissipation, and it suppresses the R mode instability at low spin frequency. But for rapidly rotating neutron stars, something like millisecond pulsars, the R mode instability can significantly affect the evolution. As far as R mode instability can affect evolution, we can compare the prediction of the theory with observations and put some constraint at which region the R mode instability should be suppressed. And the constraints which we have now is rather strong. The R mode instability should be suppressed rather strongly, but the exact mechanism of this suppression is still not well established. There are a lot of models. I have my favorite one. Other people in R mode community have other favorite one. At least we know what the shear viscosity in neutron proton electron matter is not enough. There are some references for these constraints and confronting these constraints and the theory. And one of the mechanisms which was very popular is so-called magnetic wind-up or magnetic damping. It was suggested almost in the age when it was recognized what R modes in neutron stars are unstable. The idea of this mechanism is very simple. We argue what R modes is likely to be accompanied by differential rotation if we have, or better to say differential drift of fluid elements. If we have magnetic field frozen into the matter, the differential drift will amplify magnetic field. If we amplify magnetic field, we need some energy source for this amplification. And if the subsequent amplification of magnetic field requires more energy than energy pumped to the R modes, we have the suppression of the instability. And the key question of this talk is, does this mechanism really work in neutron stars? We have two possible questions. If it really works, the situation is very simple. R mode instability is suppressed by this magnetic wind-up. We don't have any problems with R modes in millisecond pulses, nor have any problems with R modes in accreting neutron stars. And unfortunately, we don't have any detailed information on neutron stars, because the only feature which we need to work in this mechanism is magnetic field. We know what neutron stars have magnetic field. And answer no, which is my answer for this question, is what we need, another mechanism of suppression of R mode instability. And if we have this mechanism, we can confront its prediction to the theory, to the observations, and put a new constraints to the microphysics of neutron stars. And this is very interesting. I suppose it's very good for community of this conference. And what is the mechanism of this instability? In this paper by Rizzolo, they calculate evolution of magnetic field using this well-known equation. We simply put the velocity corresponding to first order perturbation of the velocity of the R modes and see what magnetic field is increasing with time in the second order and mode amplitude alpha. We also see if you look to the fluid elements, we also see some drift of these fluid elements in full agreement with this equation, and we predict the same evolution of magnetic field. And it seems very simple. If we just have the first order perturbation of the velocity, we got the increasing of the magnetic field at the second order. It seems rather robust. But what is it, in fact? In fact, this drift is well known. For more than 100 years, it's suggested by Professor Stokes, and it's known as Stokes Drift. If you have some alien velocity field with even it can be have vanishing time average alien velocity at every point, but macroscopic drift of fluid elements can take place. And this drift is not correction to alien velocity field. And what is it? Let's look to some more details. Assume what the velocity field can be expressed in this factor of amplitudes in this way. When we look to the velocity of a fluid element which stay at the moment t equal to 0 at place x0, this velocity can be evaluated by using this equation. And we can expand it in Taylor series and see what the velocity of this fluid element in the first order is equal to the time averaged alien velocity, but in the second order in magnitude, there are two terms. The first one is the time averaged alien velocity, and the second one is the Stokes drift. And the Stokes drift is not only contribution to the secular drift. This means what we can use this property, this quantity to modify the evolution of a magnetic field, and it is what is really takes place. Maybe our models require some differential rotation. It was rather widely believed that our modes are directly associated with differential rotation. This can be, in fact, it's not so. Because for instability, we need to decrease the angular momentum. The variation of the angular momentum is associated with spherically symmetric, axisymmetric part of the second order perturbation of the velocity. And this integral is indeed fixed by the condition of the Armode instability to obtain negative value of the variation of the angular momentum. But it's just integral value where we can change this function rather strongly and we don't affect the instability. Let's start to more details and discuss the R modes in Newtonian neutron stars. There are no gravitational radiation and no Armode instability. And simply demonstrate what we have Armode solution without any differential drift. This is our equations. They are very complicated, but hopefully you don't need to see too many details, but just see what this is. First order equations, this is the second order equations. The only difference of the second order equations are these red parts, which are induced by the first order solution. And the general property of a second order solution, what it can be presented as a partial solution plus general solution of homogeneous equations. This means what we can principally have a lot of second order solutions. And the homogeneous equations are the same as equations for linear perturbations in non-oscillating neutron star. And the solution for the drift is very simple. It's just an arbitrary rotation. Probably it can be differential rotation, it can be non-differential rotation, but stratified on the cylinders in this geometry. And differential drift can be absent. It's not required by the general properties of R modes. If we include magnetic field, we can see two possibilities. We can, at zero magnetic field, we have a selection solution plus arbitrary drift. It's rather simple because if we have no coupling between spherical layers, we can move it something like these parts. We have no connection and we can move arbitrarily. But if we have magnetic field, situations change rather significantly. This will be a simple mechanical model of magnetic field. And if I add magnetic field, I cannot move it independently. They are coupled and they are one time scale. And they moves non-independently, and the drift is not arbitrary, it becomes oscillations. And what is the effect of a gravitational radiation force? Which is very crucial, of course, for instability. First, recently in the paper by Friedman and collaborators, it was obtained the general second order solution in absence of the magnetic field and viscosity. They confirm what the mode amplitude is exponentially growing, the energy of a mode can be estimated by these equations, and we also obtained the drift, which is differential and depend on the cylindrical coordinate. And this result is, of course, obvious, because in absence of magnetic fields, in absence of viscosity, the cylindrical layers are decoupled, and the breaking power of gravitational radiation is different for different cylindrical layers. As a result, the different cylindrical layers move differentially. But if I add the magnetic field, the cylindrical layers become coupled. They cannot move differentially. And what we obtain? First, I will discuss the just heuristic approach. The formal derivation with very complicated second-order Lagrangian theory will be published. In heuristic approach, we have an external force, which is gravitational radiation force, which want to make differential rotation. But we also have a magnetic field which prevent this differential motion. This is a model of well-known harmonic oscillator. In absence of this magnetic field, these parts will be moved differentially for a very long distance. But if I have this magnetic field, the stronger force which I apply gives just the maximum displacement of different cylindrical layers. And these displacements can be calculated via this simple well-known equation for the harmonic oscillator with external force. The main problem is to estimate this external force, and it has two parts. The first part is axiomatic part of gravitational radiation force, calculated in this paper, and the second part is second-order magnetic terms, which can be calculated in this paper, and also co-author of this paper, and the maximum amplitude of this external force can be estimated in this one. This leads to this constraint of the maximal displacement of the cylindrical layer. If we have this displacement, we can calculate the maximum magnetic field generated by the drift. The strict mathematical derivation also will be submitted soon to the journal. We can calculate the energy density generated by a magnetic field. And the energy of a generated magnetic field is much less than the energy in the mode. It's less to the squared mode amplitude. The typical mode amplitude for R modes are restricted to the value something like 10 to the minus 4. This means what generated magnetic energy is less to the 10 to the minus 8 than the mode energy. So it's completely negligible and cannot suppress the instability. And I come to a summary. The generated magnetic field is strongly limited by this value. And for example, if we have initial magnetic field 10 to the 9, have very large saturation amplitude 10 to the minus 3, we can in principle generate 10 to the 11 magnetic field. If saturation amplitude is more realistic, something like 10 to the minus 4, it cannot do anything with magnetic field 10 to the 9. It will be no generation of magnetic field. The increase of magnetic energy cannot suppress our mode instability, at least if the mode amplitude is much less than 1. And the takeaway message is, the magnetic damping cannot suppress our mode instability, at least in case of low saturation amplitude. And this is the generally accepted model of our mode amplitude, because we have very good models of the saturation, and all of them predict what saturation should be takes place at the amplitude something like 10 to the minus 4 or even lower. And we also have a lot of observational constraints which constrain the our mode amplitude in different neutron stars, and the value something like 10 to the minus 6 and even lower. And the main message for this community probably is the last one. The mechanism of our mode instability suppression is required by observations. We know what we have a lot of rapidly rotating neutron stars, but our mode instability can prevent formation of these stars. So our mode instability should be suppressed somehow. And the solution of this problem can put very tight constraints to the physics of neutron star. And it is not limited by just mass radius curve. It's should require much more information than just depends on the pressure on the density. It can depend, for example, on the superfluid properties of the dense matter. And, for example, we can look to the poster 20, where one particular model of this suppression is discussed. Thank you for your attention.
I think we have time for one short question just before lunch. Okay, so everyone wants to have lunch, but we have an announcement. So first, thank you again for your talk. And yeah.
Thank you. Okay, so this announcement is for the people who booked the excursion. So I remind you that the excursion will start at 3 p.m. from here. So please be there in time.